Well, good afternoon. Hi, this is John Unser. I'm the project director at IACMI. We're great. We have a very exciting project that Dale Rosie is going to talk a little bit about that I know people are very interested in. What I would like to ask is that everybody mute their phones. That would be very helpful so everybody can hear the presentation, and then you can just unmute yourself if you have any questions when you come to the point in time. Okay. What I'd like to do is introduce Dale Rosie, who's our Chief Commercialization Officer, and he's going to go ahead and take over the rest of the presentation. Thanks for attending.
Thanks, John, and good afternoon, everyone. My name is Dale Brocious. I'm the Chief Commercialization Officer for IACMI, and welcome to this webinar on rapidly fabricated durable metal molds. I'm going to cover a few preamble subjects for some that might not be fully aware of what IACMI is and about. So you get a few minutes of setting the stage for why we're excited about this project, a little bit about IACMI and how we're organized. So for those of you that are quite familiar with us, it may seem a bit old hat, but always good to just put a little refresher out there. And really we'll concentrate mainly on this project around the metal molds. We'll talk about the scope of the project, the goals of the project, which IACMI core members will be participating in, what roles they'll have, how industry members can participate, and what roles we would expect or hope that industry will have. Much of that will be defined by those of you that join the project, and then how the costs will be shared, how the IP will be shared. So my preference would be to wait till the end for your questions. If there's something that's just burning and you need a clarification, you can unmute and feel free to ask that. So I'm going to start out by, obviously one of the things that as IACMI, we're well aware of the opportunities for advanced composites, particularly carbon fiber composites, but also other forms of composites, whether those be in molding compound form, prepreg form, injection molding form, or otherwise. Up to 50 to 60% weight reduction versus steel, and up to 40% versus aluminum. The flexibility that composites offer, or something that's very attractive. Tool investments, while lower, are still high, but there are cost savings over stamping tools. And then there is this opportunity for parts consolidation. This is one of the big value propositions of composites in our industry. One of the things that we talk about, people talked a long time about all carbon composite cars and other, full composite structures. But I think we're entering a world where we really need to think smartly about multi-materials design. BMW's kind of led the way in the automotive here, where they've taken 16 carbon fiber parts, molded parts, put them mainly in the periphery of the vehicle to give the vehicle overall torsional stiffness. But by doing so, allowed them to use a lot more aluminum and a lot thinner gauge steel in a lot of areas. Basically taking 15 to 20 kilograms of carbon fiber and converting that to 146 kilograms of overall weight save by downsizing other systems. And we think this is probably, a real opportunity going forward. And notice that they've used multiple different processes on this, 4 different technologies to do this work. So it creates opportunities. So if we think about what that means, if we look in the world of automotive, and there are obviously opportunities outside automotive, but if we look at a global market of 90 million units and 10% of the vehicles could go to this, assuming we can drive the costs down to make that attractive, at 15 kilograms of vehicle, you're talking 135,000 metric tons of carbon fiber. When you add resin to that and make those into parts, you're talking about 500 million pounds, half a billion pounds of material per year. That's just a 10% market penetration with this sort of approach. But the key thing here, and the thing I really want to emphasize here, is the number of parts. You're talking with these kinds of parts and their average weights, up to 144 million molded parts that have to be done every year. And so you're talking about an awful lot of tools to make those kinds of things. If you think about what this really means, you put this in context of the current market for carbon fiber, which is only about 80,000 metric tons for all applications. That includes Boeing, Airbus, sporting goods, all current automotive applications, wind turbines, whatever. So we're talking about something that would almost triple the current market at 10% penetration if you got to 20 you'd have a 4-time market. So real opportunity there to get to there. Some of the barriers that we see, cost is the biggest barrier. The cost of composite parts and so forth. One is certainly attributed to the material and the high price of carbon fiber, and there's a lot of companies, and as well as IACMI, addressing that. The amount of recapitalization needed, can't get everybody to throw out all their old processes. So, if you're thinking of stamping situations, how can we stamp carbon fiber or recapitalize or use some of those? But there's a tooling aspect to that as well. How do you, the retooling that occurs for that. And then the qualification processes, which tend to be fairly lengthy. In terms of speed, continuous fiber lamination is an issue. Material transfer robotically is not as fast as it needs to be. And then the big thing is this prototype process, and this really comes into where the tooling is important. Is if we're doing iterative prototyping, the cost of building multiple tools to do that prototyping really lengthens product development, but it adds a lot of cost as well. From an understanding standpoint, many of our designs today are overly conservative. So we still got to learn how to design to a true minimum mass and take full advantage. That'll take a lot of cost out, cycle time, et cetera. We need more confidence in our manufacturing processes. So the ability to predict what those processes can do and then the resulting performance will help us to do that. And then, of course, how do we repair composites? And then from a sustainability standpoint, carbon fiber manufacture is energy intensive. It takes a lot of kilometers to drive a car before you can get the value of that CO2 back. And so driving some of that out of the process is very important. The ability to reuse the material. First, let's try to generate less scrap in the factory. Today we take a lot of roll goods. We cut that out, take 30% of it and put it in the garbage, or we have to find a way to recycle it. We don't have that infrastructure in place, but it's coming about, and we're trying to understand that, and as well as the data on the properties of using that recycled fiber. So what this really requires an integrated approach to solve this problem, to drive the cost down, drive the understanding up, to and to make the value proposition of composites a lot more attractive. So whether that's materials, the manufacturing processes, the design and simulation, all of these need to be worked in parallel. And that's what IACMI is about. So what is IACMI? It's a not-for-profit owned by the University of Tennessee Research Foundation, headquartered in Knoxville. A number of you on the phone call are already members or considered being members. 155 members in the consortium, 125 of which are industrial entities. So it's a large amount of the value chain that's involved, all the way from resins and fibers up through OEMs. It is a DOE institute. It's sponsored by the Department of Energy with $70 million in allocated funds over a 5-year period. We're just past the 2-year mark, so there's still almost 3 years to go. And then there's $180 million from various states and other industry partners. It's broken down into 5 areas, technology focus areas. Composite materials and process technology is headquartered out of Tennessee area. The design, modeling, and simulation out of Indiana. Compressed gas storage out of Ohio. Wind turbines in Colorado. And the vehicles was, as you might naturally think, headed out of Michigan. And there's a number of research institutes or research laboratories and strong university institutes involved in this across the Midwest and out in Colorado. We've got a couple of satellites out on the coast. So all of these entities have a long history with composites and bring a lot of complementary assets and capabilities to make all of this come together and work. So while there's some assigned focus, there's a lot of crossover, a lot of integration that's occurred here. The key thing is that we're really looking at is how are we able to take these technologies and scale them throughout the manufacturing process, all the way back to the fiber level, to maybe prepreg, maybe being able to make prepreg, for example, do intermediate scale molding of that on say a 750-ton press to understand the behavior and the properties, and then go all the way to full scale operation in Michigan at our scale-up facility. And across the bottom line, the modeling and simulation that needs to occur across all of those scales to be able to realize cost-effective production of these materials. So when we talk about the opportunity, obviously we have the opportunity to reduce weight, improve performance, this consolidation of parts versus what are traditionally metallic solutions. Also, composites also are capable of replacing other types of materials, but mostly we're thinking about them as substitutes for metal structures. In order to get the confidence by the OEMs, it's necessary to build prototypes that are fully functional and test those to verify that, largely for liability purposes, but to get that confidence so that we can get them to convert to composites. Having been in this industry for 30 plus years, a lot of the impediments that people talk about when I've tried to help them convert something from metal to plastic, metal to composite, is the cost of the prototype tooling. It's a big deal, and the length of doing the prototype tooling. That's a major impediment. And then, even if you get past that point, then you have the tooling costs that are involved, this bit of recapitalization and those lead times, which are, for metal tools, are often in the order of 26 weeks or more. Those just extend the product development cycles. It requires you to lock in your designs very early, and don't give you much flexibility to alter those designs once you've made that commitment to the tooling. And they typically require large volumes and long production runs to justify the amortization on that. So the bigger the tool, the bigger the cost. Cliff Eberly had shared this with me at one point. There's a big truck hood that rumored that this tool set altogether, when it was all finished and done, was $7 million. For SMC truck hood. It's a pretty big nut. And I'm not suggesting that we're going to be able to tackle something this size right away, but eventually, the idea that you find a way to take a lot of that time and cost out of getting to large tools. Of course, we have to start with small tools. Okay, a lot of you are familiar with the big area additive manufacturing at OR&L. This was the Cincinnati machine gantry system that has an extruder that does the polymer deposition. The Shelby Cobra was something that's pretty famous, been out there along, quite several years now. It was kind of really brought a lot of spotlight on OR&L and the ability to do high rate polymer manufacturing, hundreds of pounds per hour type of approach versus small printing. Other work that's been done, printed house, printed Jeep, a lot of other structures that have been done in thermoplastic, and it continues to advance there, including some work in high temperature polymers like PPS or PES or PEEK, carbon fiber for high temperature things like maybe for prototype tooling or autoclave tooling. But that's been augmented now by work that OR&L has done in 3D printing of metals. Now OR&L has a lot of capabilities to do 3D printing on small scale of metals, powder metallurgy and so forth. So the thought was, how can we get to the kind of rates we need to get to with metal printing, like we've done with polymer printing. So some of these early results are very promising. This was an example of an excavator that was done where the cab was 3D printed in polymers, and then in what they call the stick, or the part that does the work out in the digging end of the excavator was 3D printed in metal. And I've got a video of this to show you that being printed, but that's steel out there that was printed from scratch, not being welded together and machined back. A little bit of a video here that you can see of that. This is courtesy of Suresh Babu from the University of Tennessee, Knoxville. This was done at OR&L. You can see the video up here of building of that particular element, and it comes together pretty quickly. It's obviously a time-lapse video, but there's a lot of metal being added and deposited, very similar in the way that we do the polymer printing, if you've seen that. So it's you get kind of a corduroy type surface on that, and I'll have some photos that kind of hint at what that looks like. So all of those, this will require a little bit of machining at the end, but it's not nearly the kind of thing where you take a giant steel block and do all subtractive manufacturing on it. And there's a lot of science that goes into this, with looking at the microstructure of it at various points and how that changes. At this point, we certainly haven't, done everything with every kind of metal, but certainly points the way toward being able to get down this path. So let's talk about the project that we want to do, and this is really about trying to make molds with this. Compression molds, eventually injection molds, certainly autoclave tools, but that can be done in a rapid fashion and hopefully at a much lower cost. So the big objective is to get the cost and lead time of production down. We're not necessarily at this point trying to attack the Class A surface part of that, although that opportunity is still out there. But for many parts that don't quite require a true polished Class A, we think this has opportunity. But the key targets would be to reduce the cost by at least 50% over conventional subtractive metal mold making, up to an 80% lead time reduction, maybe more, again, depending upon the complexity and size. We're not talking about just doing small things. We think that within the next couple of years, we want to target getting up to a 50 square foot surface, so something that is 7 feet by 7 feet or larger, so 2 meter by 2 meter part surface with good depth of draw, so not just flat panels, but able to get at least an 8-inch depth of draw that would cover a lot of parts that are out there in the automotive space and in other markets. We definitely want to be able to look at complex features. How do we get the ribs in? We obviously will need ejector pins, and then, can eventually build these with slides as well. Don't know, because of the pressures involved, whether we can get all the way up to the high pressures of injection molding on tools this size, but most injection molded parts are well below this size. So we believe that we'd be able to get to up to the 10,000 psi peak pressure that you might need for injection molding. Durability is something we're really going after. So we're not talking about trying to do this with mild carbon steel, but with tool steels. How do we do this with tool steel to build these up and get that kind of durability that you need for the surface, up to say 2 million molding cycles at 2,500 psi. So this is the goal of this project. Every tool needs maintenance. The chrome will wear out. You'll get some erosion in some areas, even on our best tools today, depending upon the material you're molding, the pressures you're molding, and the flows in that tool. But to be able to get to that same level of or better of maintenance, this may allow us some interesting surface technologies with respect to what kind of alloys we might be able to put at the surface, instead of having to use totally monolithic materials. And then because we're actually building this up and then machining some way, they offer some opportunities for minor design changes along the way, where you could go in, cut something away, come in and 3D print the area that you needed to modify, and then bring that and then finish that off and get that with the new dimensions. So some opportunities there. So in addition to that 3D printed stick, Ornell has done some work, some initial work. These are probably, I would say, on the order of about 18 inches by 18 inches, or between a foot and 18 inches in each dimension, looking at can-do print tooling. So if you look at this, you can see that there are some ribs that are along one edge of it, so you can see the direction in which it was printed, and then the surface was machined back to this. There's a little bit of surface porosity in these tools, but it's overall, for a first cut, pretty interesting, pretty attractive on that. And we've actually taken some long fiber thermoplastic that's come out of an extruder and then stamped out some thermoplastic parts. So while the tool wasn't being heated and cooled actively in this situation, we were able to mold some parts on it, just as an example. Another picture of that die set, or a die set there. One of the things that you look at this and you can see the opportunities that if you can build hollow structures there, where you have the face sheet and then what's inside can be behind those face sheets, can have some various structure that you need to be able to handle the pressures that are there, but also create cavities that allow you to do things, for creative heating and cooling solutions, for example, or maybe you cast a lower temperature metal such as aluminum or copper or an alloy of those behind in that annulus, and then put your heating elements inside that. So some of those aluminum and copper, for example, have much higher thermal conductivity, so it might enable much faster molding cycles and so forth. So just opportunities to get really creative with this sort of technology. Of course, there's always the opportunity just to build it, 100% monolithic, but I think this opens up design space a lot for tools. So as we think about this, and we're still working through the timing on this, on how long it takes to get there, but we see it as a progressive sort of effort. Starting with something that's a relatively flat tool like to compression molding at 1,000 psi and achieving at least 100 cycles, followed by higher pressure and higher cycles. So we may be able to get through these fairly quick, these first couple of ones, and then to look at something that's a bit more complex, maybe a double dome shape or some other shape that we as the industry comes together says we need to do, but include some ribs and other features in that, and then again demonstrate that at similar pressures and cycles, and then move on up. Try to get on up toward that 50 square feet, and progressively test it at higher pressures, and then continuing on longer cycles. At each step of the way, we need to understand what we need to modify, what needs to be fixed, what other features need to be added. So this is just a preliminary type of approach over a several year period to get there. So the project itself, so this is an open call. What we're looking for is for people to indicate their interest by the end of September of this year, so that we can try to get the project agreement written up and get the project underway by the first quarter of 2018. If people, new members join IACMI, we're looking at the opportunities early stages where the technology levels are still relatively low and where the applicability is still at early development stage, to be able to continue to join maybe for the first year. Any additions to that after the first year would have to be by consensus from those who are already in, who have made the investments in time and cash to participate. So in order to participate, and many of you that are on the call are already involved in IACMI projects, therefore you've already signed a master sub-agreement, which is a one-time agreement between the industrial member and IACMI that governs a lot of just the overarching project rules. And then once the project agreement is in place, then each participant will need to sign that project agreement, not all at once, but as they come on board to be part of the project. Okay, IACMI has a number of core partners. You saw an earlier slide where I showed the map. And a lot of capabilities that can be brought to bear here in order to bring neural science into this and to help make this whole process of 3D printed metal tools more robust. The technology that you saw, the video you saw, was being done at the Oak Ridge National Laboratory at the manufacturing demonstration facility in Oak Ridge, or in Knoxville. So the main thrust of the 3D printing would occur in that facility, and then the initial machining would also occur there. Although those tools could be sent out for machining at other shops or polishing or that kind of thing. Our Purdue University site, where modeling and simulation is, they've done a lot of structural thermal analysis of 3D polymer printing so far, and we would look to them as well as to ORNL to help us do that structural and thermal analysis modeling of the printing process. What are the residual stresses that are in the part? What kind of warpage might we get? And those sorts of things. Our friends at Vanderbilt, where most of our NDE work is headquartered. One of the things that you'll have in this is inherently, if you've dealt with a lot of cast parts, there's subsurface porosity that can occur. We expect there might be some in this case, but the ability to actually map the surface for surface porosity that can be seen, visually or through some other NDE technique, but also maybe through thermography or other technology, detect that porosity that might exist, a millimeter below the surface, that's going to give you a problem when you start to go into molding cycles and so forth. So we can map that and go in and fix those areas before the tool ever leaves the shop. And at the University of Tennessee and at Michigan State, the scale-up facility and our Corktown facility, is where we would start by doing the small-scale molding trials and validation. So, as we're developing this, we at least start those there before we send them out to industry to test in your shops. Industrial participants, clearly what we need to do is we've got a starting idea of what types of requirements we're going to need to have. But I think one of the early tasks of this will be to convene all the industrial participants and agree upon what are the particular performance requirements in terms of surface finish, durability, hardness, temperature requirements, and so forth. What are we trying to get to, both in the early stages and longer term? And then how can we develop that transition strategy to be able to take this technology to the field? So finalizing that project plan, circulating that, socializing that, agree on what the schedule, the budgets, what the stage gates are, what are our metrics, our go gates, milestones, and so forth. What are the representative parts we want to look at? So what are the tool geometries that are of interest to industry? That we're trying to do. We're not trying to solve. We don't see this as a solution for every part that's out there, but certainly for a wide range of parts, perhaps a 75% or so. There's possible solutions out of this. And so we would certainly look to say which are the ones that are going to tell us and give us the confidence that this technology has real value. We would expect that you as industry would want to validate this technology in-house, under real conditions with the types of materials that you buy and use. So, the ability to, if we're going to be able to print tools, we could print 4 or 5 copies of them, and distribute those to some of the industrial members to go test and try, and then come back to us with feedback on that. Put it, so in that case, it might be something that you've got in production today that you want to give it a try as a backup tool or as a sister tool to something that's already there, where we can do that kind of comparison and validation. And of course, there'll be other roles as you decide. If we have tooling shops that are part of this process or this product, that can build these. There might be machining and polishing opportunities there. There's lots of technology options for heating and cooling opportunities out there, whether that's strictly through fluid heating, electrical heating, air impingement, induction, whatever, all kinds of opportunities there to play in that role. So it's going to require some amount of co-sharing of this. There will be federal funding and state funding available out through the IACMI process, but typically we're looking to get, we need to get a one-to-one industry funding to our state and federal funding. So we think this project has a budget of about 5 to 8 million years over 3 years. Whether 3 years is the right length or not will be determined by the team as we come together. Obviously, we want to get there as fast as we can. I've certainly challenged the lead project investigators on this to PIs to try to see how far we can get in the first 2 years. So we've been expecting to try to get with enough partners involved, $1 to $1.5 million of cost share, of which 1/3 would be cash and the rest in kind. So everybody that participates would need to commit some in-kind participation. The large business participants would be the ones providing the major, cash contributions, and if an SME is participating but not in an in-kind fashion, would probably have some cash requirement, although it wouldn't be a very large one, but it would be something to make sure there's a buy-in there. So again, it's going to come down to simple math. When we get to a budget, if we've got 50 companies participating, it's probably going to look pretty attractive on an annual basis to those companies participating. So what do you get, at the end of this? So IACMI has an intellectual property management plan. It's available on our website. So, it's certainly something that you're aware of if you're already an IACMI member and have signed the master sub-agreement. But basically, if you develop IP related to this technology outside the project, you own that. But everybody who's signed the project agreement and made the required cost share contributions to the project will have what's called undivided ownership in the jointly developed IP, which is the IP we jointly developed together, which would allow you to practice and license that. If there's with there is a U.S. manufacturing clause that says that these technologies need to be commercialized first in the U.S. before they're commercialized outside the U.S. Any technology developed by a core partner, exclusively by ORNL or Vanderbilt or others, that technology will be licensable on a limited exclusivity basis first to all industry partners that have participated. So it's a pretty generous IP. If you're in, you'll have the right to go practice this technology in your business. And certainly we can answer further questions about that. So that concludes the presentation at this point. And we'll open it up to questions. If you're interested in the project, we would ask that you contact one of the four of us to express that interest and make sure we get you on the list so that we can move forward. Okay. So if any of you have questions, you can unmute your phone and ask away.
Can I ask a question? I'm Patrick Kwan at Michigan State.
Sure.
We have developed a technique based on what they call binder jet printing, where X1 is, I don't know whether they are the member, but we use their technique but modify substantially to make the full density part of stainless steel. And we are in a process going towards a tool and die steel. So we have a technology that I think IP will be issued very shortly that can fully densify. We're talking about 99.7% dense, which is more like full density. We can make a part any shape, including internal channels, with a relatively good surface finish. In addition to that, because it's a binder jet where we are heating up this thing all isothermally, there is no residual stress, which means we can machine it and make it into a much finer structures or much better surface finish. So we have that technology available, and I wasn't sure how we can participate as part of this IACMI.
Okay. Well, as MSU is already a core partner of IACMI,
right.
So is that. But Suresh, do you want to address the differences here? What we're trying to do that's different than maybe what Patrick
I think the binder jet is a very good example to make small molds and everything, and also there are beds to make it larger scale. The only question would be the cost factor per pound basis. So the powders which you need to buy, or if we compare it to the welding filler wire, they are much more, quite a lot of 1 order of magnitude difference in cost. That is what my current understanding is. I may be wrong. The powder cost may be cheaper than the wire cost. I don't know that.
Well, there's more material available for powder. But in terms of cost, I don't think that may be a big issue because when we make these powders, we can only do the important sections with the powder. The rest of them we can just use a solid metal.
Hey Patrick, this is John Unser, the project director at IACMI. I think we do have interest in it from IACMI standpoint, but I think I think it'd be good to take it offline and come talk to me about it a little bit.
Okay.
So, because I think there's a project that we could do. Might not be the focus of this specific area,
okay,
but I do think we have a project that we've got some other projects going on that we should talk a little bit more about. So let's take that one kind of offline and see if there's any other questions from the industrial partners who can ask.
Okay. How do I contact you, by the way?
I'm John Unser. junser at IACMI.org. I'm the project director at IACMI.
Okay.
And you can email me, or you can talk to Larry Drizel and get my contact information through him too.
Any other questions on the process?
Yeah, this is Jeff Conley from Ford Motor Company. And I really don't have a question. Are you going to send this presentation out, or is this confidential to?
The presentation will be on our website, and it's actually being recorded. So, so all of the presentation will be there along with the recording. So you can share that with your colleagues.
And what's the website?
It'll be on the IACMI.org, and
Okay.
we'll follow up with a link to that to everybody that signed on today and at least gave us their email.
Okay. Thank you.
Sure.
Well, if nobody else has any more questions, feel free to contact any one of us on the screen, and we're definitely moving forward with this project, and would love to have some strong industrial partners to work with. If you know of any other, you do have to be a participant of IACMI to be a member of it, but we can definitely work with you to become a member if you want to. It's not that hard of a process, other than and then we can work through what we call the master sub agreement to do. Dale, anything else you want to, or Suresh, want to talk about?
Yeah, I think the one thing that I would like to point out is that this is this is not small scale metal printing, that as we typically have seen. The idea here is to get to very large scales.
Yep.
And do that at a fraction of the cost of typical 3D printing of metals.
Yeah, that's correct.
So, John, I might add, this is Cliff Everly. I just might want to make all the participants aware. We do have a call out for other technologies to improve the cost of tooling.
Right.
This project is specifically aimed at using metal additive, but IACMI has, in its recent release of its RFP, we're open to other methods if people have something else that they would like to propose.
Yes. And if you have any questions or anything like that, you can talk to me about what those are, or look on our website to find what our proposal process is.
Right.
Okay, thank you.
All right, thank you all for attending.
Thank you.
Thank you. Bye then.